Next, we talk about differentiability. So we say a function is differentiable when the derivative does exist. So by definition, derivative is defined by limit. Once the limit exists, we say the function is differentiable. So a function is differentiable at x equals a if f prime of a exists. So you look at the limit for this expression, and once the limit exists, we say the function is differentiable. We also say f is differentiable on some interval if it is differentiable at all points on the interval. So quick example. Let's use this function absolute value of x. The graph looks like this. Whenever x is positive, we have copy of y equals x. And then whenever your x is negative, we have negative x. So graph looks like this. For almost every point, we can draw tangent line. So there shouldn't be any obstacle for us to draw tangent line. So we can say your function is almost differentiable, but x equals 0. So look at this point. Can you imagine any kind of tangent line? Actually, no tangent line is possible at x equals 0. So in that sense, your function is differentiable everywhere but this. So we can say f is differentiable on entire number line minus this point, or you can split your set into two intervals from negative infinity to infinity, and from negative infinity to 0, and then from 0 to infinity. And you can join them with union symbol. Okay, and then one quick observation. If your function is differentiable at a, your function is really nice, then you can talk about continuity. So this theorem concerns differentiability and continuity. If you compare two conditions, which one you think stronger? Differentiability is stronger. So if your function is differentiable, then your function is automatically continuous. The function is why? Well, if you can think of this way, if your function is not continuous, then your function is not differentiable. So you can use counterpositive statement to see if the function is not continuous, then your function is not differentiable. Okay, so differentiability is way stronger than continuity. Okay, if you are given the graph, or if you know the graph of the function, you can tell differentiability immediately. So look at this first case. Our graph has some sharp turn or kink or cusp. In this case, your function is not differentiable at those points. So if the function has a sharp turn or cusp or kink, then your function is not differentiable at that point. If your function is not differentiable like this, any kind of discontinuity, then your function cannot be differentiable. Then f is not differentiable at that point. And sometimes, this is quite rare, but sometimes your function may have vertical tangent line. So tangent line like this. In this case, when you think of slope of the tangent line, then the tangent line is vertical, so the slope is infinity. Remember, f prime is defined by limit, and the limit becomes infinity. In that sense, we say the limit doesn't exist. That's why we say f prime doesn't exist. So consequently, we want to say this function is not differentiable. So f prime of a does not exist because this limit is infinity. Okay, one more quick example. Suppose we have a function x squared minus 4 inside absolute value symbol. Well, the graph of x squared minus 4 is parabola passing negative 2 and 2. Once you take absolute value, then we are taking everything positive. I mean, the result of this absolute value must be positive. So look at this portion below x-axis. You are taking this portion and somehow you are making that positive. Geometrically, that means you are taking the portion of this parabola below x-axis and flip or reflect about x-axis. So we have graph So that is the graph of absolute value of x squared minus 4. So once you reflect like this, you have 2 points where we have sharp turn. So we can say this function is not differentiable at those 2 points. So x equals negative 2 and 2. So this function is not differentiable at those 2 points.